Hello, this is the fifth video in a series that I'm calling Transformations of Random Variables. And this one we're going to look at a discrete multivariate case, specifically sums of binomial random variables. So in our example, we're going to let x1 be binomial n1p, x2 be binomial n2p, they're independent. And we want to find this, the sum of the random variables. So we're interested in y1. And so we have to we're going to introduce another variable called y2, and then we'll find the joint distribution of y1 and y2, and then we'll sum out y2 to leave the joint the distribution of y1. And we're going to do that in a unique way here. So to back solve for x2, we just get y2. That's kind of a duh moment. And then to back solve for x1, we get y1 minus y2. Okay. So we want to find the joint distribution of y1, y2, the distribution of y1, and then the conditional distribution of y2 given y1. So to find the distribution of y1 and y2, that means the probability that y1 is little y and the probability that y2 is little 2. But if we substitute in our change of variables, or our transformation, we get this. And then this here is a joint distribution. So it's the probability that x1 plus x2 is equal to little y1 and x2 is equal to y2. And the reason I stress it like that, it's the and, because if x2 is y2, that says that this one has to be y2, and we could subtract it to the other side, and that's what we do here. Well, now this becomes a probability in terms of x1 and x2, and they're independent, so we can break this up into the product of their marginals. And when we know the distribution of x1 and x2, they're binomial. So this first one is this. It's a binomial, and where you plug in y1 and y2 in for the variable. So it's n1, choose this, p raised to that power, 1 minus p raised to the n1 minus this, and then when you distribute the minus, it becomes a plus. And then you plug in y2 for the second, for x2, the distribution. Okay. Well, now we need to simplify this a little bit, and so we move the combinations out front, and we can combine the p's, and the y2's cancel, leaving just y1, and then this is common, so we can combine those two, which then ends up being n1 plus n2 minus 1. And this is where y1 is between 0 and n1 plus n2. And x2 is between these two variables, the maximum of this and the minimum of this. And now we're going to spend a page and a half to make sure what this even means. And we are going to simplify this, which will then help us find the conditional distribution. So this is it. This is finished, but this can be simplified just a little bit in what we'll do here. Okay. Now to do this, I like to draw pictures or illustrations of what's going on. And so here is the original. We have x1 and x2, and they're independent. x1 goes from 0 to n1, and x2 goes from 0 to n2. Now they are discrete, so we're talking about points, but I draw it like a continuous region. And then what I do is I want to map this into y1 and y2. And there's two different cases, and whether n1 is bigger or n2 is bigger. So this first case, we'll assume n2 is bigger, and then each of these boundaries is when you do the mental math, they're mapped into those specific regions. Okay, and so it goes to N1 and then up to N1 plus 2. And this one, since N1 is bigger, it goes past it and then up, and then it goes over to N2 each time and then back down. But in either case, though, it's the same. So now to find the regions of these two, there's kind of two different strategies to do this. You can let Y2 be unrestricted, meaning it goes from 0 to N2, and then you find the restrictions on this. So, or you could unrestrict this, say Y1 is between 0 and N1 plus N2, and then you find the restrictions on Y2. And in this case, that's what we're going to do, but it really doesn't matter. So now here we have, we'll do the boundary, the below boundaries. And I'm just going to look at this one, but it's really the same as this. So this line here is Y2 is 0. And this line here is Y2 equal to Y1 minus N1, okay? And if we let Y1 be unrestricted, then Y2 has to be above these, right? So if this line technically goes on forever, and this line goes on forever, so whatever the maximum is between these two, so like if it goes on forever, well, we want this one because it's bigger, and over here it goes down, but we want this one because it's bigger. And that's what this maximum is. It's the maximum of 0 and this line, okay? And so that's why it becomes the maximum. And now it's the same way for the minimum. So Y2 has to be below, in this region, which is below these two. Well, this one is the Y2 equal N2 line, and this one is the Y2 equal Y1 line. So in a sense, this goes on forever, and this goes on forever, but we restrict it to this region. And so if this were to go on forever, we actually want the minimum. If this were to go, we want the minimum of those two. And that's where we get the minimum of Y1 and Y2. So now if we generically call this U and this V, then our so that's how we come up with this right here, this region, okay? Okay, so then we're done. This is the joint distribution right here with these restrictions. Now to find the marginal of Y1, which means the probability that Y1 is equal to little y1, we want to sum out Y2. But Y2 has these crazy boundaries, so how are we going to do that? Well, generically, we know this function, which is this and that, and we're going to sum out Y2, but since these don't have Y2 in the sum, they're going to come out in front of the sum. So we're summing this. But if you think about U and V, there's 4 different possibilities where we go from 0 to Y1 and then 0 to Yn2. There's 4 different situations. So we're going to look at those individually. So there's 4 different combinations of U and V. But before we look at those, I want to introduce something called Vandermon's identity. Now I have a video on this proving this relationship. So if you search Vandermon's identity in my videos, you'll see a proof of this. But for this video, we're just going to assume it's true. So if we sum from K to R of these, that is equal to M plus N, choose R. So now if we look at the one case where the maximum is 0 and the minimum is Y1. Okay, so that means we're in here, this region here, or it would be this region over here. So we're summing from 0 to Y1 of this quantity. which was this quantity. Well, this is exactly like Vandermon's identity. So this is equal to N1 plus N2 choose N1 or Y1. So this simplifies to this when we're in this case here. So now let's look at the next case where the max is 0, but the minimum over here is N2. Okay, so we plug in 0 and N2, and it's of this right here. This is what we're summing. So if you look back here, we're summing this, but we plug in the next case for U and V, which is 0 and N2. Now, this is all we want to sum, so it's kind of silly to say, you know, if we add 0, it doesn't change this sum. That's a true statement, but we're going to add a well-chosen 0. Okay, so this stays this same, but then this term here, since, you know, once we get Y2 gets to N2, you know, it's kind of at the last spot, but let's go one more to say N2 plus 1. Well, since this number is bigger than this is 0. Okay, and then we go to N2 plus 2, and then N2 plus 3, into whatever N or Y1 is. Remember, the minimum is N2, so this is bigger, and we're just going to increment by 1 by 1 by 1 until we get to Y1. But each of these is 0 because this number is bigger than that, and by definition that is 0. So we're adding 0. But if we look at this sum as a whole, we're really going from Y2 equals 0 to Y1, right? That's what we're doing. Well, again, this is the Vandermon's identity. So this equals N1 plus N2 choose 1. And now, in the interest of time, the other two cases, you can do a similar argument, and it also equals N1 plus N2 choose Y1 using the Vandermon's identity. So the marginal distribution of Y1 is this distribution here. And if you note, that's a binomial N1 plus N2 choose with parameter P. So now let's look at the conditional distribution of Y2 choose Y1, or given Y1, which is this probability, which can be written like this. Now we just derived both of these cases. So we put the densities, you know, this is the top and that is this, and then things cancel out and we're left with this. Well, on close examination, this is a hypergeometric with N1 and N2 as the population sizes. Well, that's all I have for today. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.